recall, in the previous lectures we talked about the various number systems: decimal, binary, octal, hexadecimal, and we mentioned one thing, that binary number system is important from the point of view of circuit design, specifically digital circuit design. So, in this lecture we shall try to first motivate you why that is so, and secondly we shall show you or tell you that how to represent arbitrary numbers in binary. Like, so far we did not consider negative numbers. How do we represent negative numbers? We assumed all numbers to be positive. Okay? So, we shall be talking about these specific things in the current lecture. So, this lecture is titled Signed and Unsigned Binary Number Representation. So, let us first motivate ourselves why binary numbers are important, why do we use them. So, I just mentioned that binary numbers are important from the point of view of circuit design, but why is it so? Okay, to answer this question you will have to understand how circuits are designed and implemented. Modern day circuits are invariably implemented using basic building blocks like transistors. They are typically MOS transistors, metal oxide semiconductor. Symbolically, a transistor is represented like this. Depending on what we apply to a terminal called gate, there may be a current flowing between the other two terminals, or there may not be any current flowing. So, transistor acts like a switch. Depending on my control input, G can be regarded as a controlling input. So, it is either conducting or non-conducting. There are two states. Now, in a modern day VLSI chip, there are billions of such transistors. That means, there are billions of such switches, very small in size. They all turn on and turn off in synchronism depending on some external event or applied input, and they realize some functionality that we want it to realize. Okay? So, as it said, a switch can represent two states, either conducting or non-conducting. Now, as an analogy, binary number system also has two states or digits 0 and 1. So, if I can represent the conducting state as 1 and the non-conducting state as 0, then I can say that a MOS transistor, the state of a MOS transistor represents a binary digit. It is either conducting or non-conducting, means it is either 1 or 0. So, there is a 1-to-1 correspondence. Similarly, other conventions you can follow. This is what I just mentioned, open switch is 0, closed switch is 1, or you can talk about voltages. At some point, if the voltage is low, you can say it is 0, if the voltage is high, you can say it represents binary 1. Then absence of current or presence of current, like the example I took, or in some circuits nowadays we use light for the purpose of computation. So, if there is no light, it can represent binary 0, if there is a light, it can represent binary 1. This is the basic principle behind photonic communication. Like we know, nowadays optical fibers are used for long distance high speed communication. The basic principle is like this: you send light and you sense light at the other side, whether light is coming or not coming. So, bits can be represented depending on the presence or absence of light. Okay. So, in this course, because we are talking about digital circuits, we shall be concentrating on binary numbers. Now, let us introduce some definitions. A single binary digit, which is 0 or 1, is termed as a bit, as we also mentioned in the last lecture. Now, when you have a collection of 4 bits, that is called a nibble. collection of 8 bits is called a byte. Next higher thing we call it as a word, but of course, the definition of word is not well defined. Depending on the context, 16 bits, 32 bits or 64 bits can be considered as a word, but the definition of bit, nibble and byte are well defined. It is 1, 4 and 8, that many bits, right. Now, let us talk about representing numbers in binary. So, the question that you are trying to answer is that suppose we are representing a binary number in n number of bits, let us say n equal to 16 or something, let us say n equal to 16. Now, I may want to ask a question that in 16 bits, how many distinct numbers can I represent? This of course, I want to know. Like in 4 bits, you already seen earlier, you had seen earlier that when you had talked about hexadecimal numbers, in 4 bits, we can represent number from 0 up to 15. Octal for 3 bits, 0 up to 7. So, my question is for n bits in general, what will be the range of numbers, how many total numbers I can represent? Okay. So, it is a simple combination calculation, like each bit position, there are 16 bit positions, right. So, each bit positions can be either 0 or 1. So, there are 2 combinations. Second bit position again 0 or 1. So, you multiply 2 into 2 into 2 up to n times. So, you get 2 to the power n. This is the total distinct numbers you can represent. So, you recall for hexadecimal n equal to 4, you had numbers in the range of 0 to 15. So, how many numbers are possible? 2 to the power 4, 2 to the power 4 means 16. So, total 16 numbers could be represented. So, here for n bits, I can represent total of 2 to the power n numbers. Okay. Now, next question is how to incorporate sign in a number. Numbers can be unsigned or there can also be a sign associated with a number. So, an unsigned number will only have a magnitude, but no sign, but signed number will be having a magnitude as well as a sign, which will indicate that it is either positive or it is negative, right. Okay. Let us first talk about unsigned binary numbers. Now, we just now saw that in n bits you can have 2 to the power n distinct combinations. So, the minimum number that you can represent is 0, all zeros, and maximum number is 2 to the power n minus 1, all 1. You think of hexadecimal, 0000 means 0 and 1111 means 15. For octal, if you take n equal to 3, the 8 distinct combinations will be 000, 001 up to 111. If you count, there are 8 combinations. 000 means 0, 111 means 7, which is 2 to the power 3 minus 1, 2 to the power n minus 1. Okay. So, this table shows that as the value of n increases, so how much is the range of the numbers change? For 8 bits, it will go up to 2 to the power 8 minus 1 means 256 minus 1, which means 255. For 16 bits, this is 65535. For 32 bits, it will be about 4 billion. So, you can say numbers up to 10 digits can be represented, but in 64 it will be even larger. So, if you just calculate this, it will be approximately about 21 digits, so large number. So, as the number of bits increases, the range of the number increases very rapidly. Okay. So, as this table shows, this we have to remember. Now, this already we have talked about earlier, this I am showing it in a you can say in a mathematical form. Let us say I have an n bit binary number where the digits are represented as, this is an integer number, no fractional point, B0, B1, B2 up to Bn minus 1. B0 is the least significant bit position and Bn minus 1 is the most significant bit position. So, the weights will be 2 to the power 0, 2 to the power 1, 2 to the power 2 and so on. So, when you try to calculate the decimal equivalent, you multiply the digits by the corresponding weights and add them up. Sorry, like B0 you multiply by 2 to the power 0, B1 by 2 to the power 1, so on, Bn minus 1 by 2 to the power n minus 1. So, in binary we have seen that each digit position has a weight which is some power of 2. This way you can calculate the decimal equivalent. Okay. Just an example for n equal to 4. For 4 digits, just like hexadecimal. So, if you express all possible combinations in binary and try to convert them to decimal, you will see that the range of numbers you can represent will start with plus 0, it will go up to plus 15. These are considered to be unsigned number, that means positive, no sign. Okay. This already we have seen for hexadecimal numbers, the same thing is there. Now, let us come to the issue of sign. So, in most of our calculations we have to deal with both positive and negative integers. So, now the question is, how do we represent negative numbers means in a system or in a circuit, and how do we manipulate on them. Okay. So, the answer to this question, how to represent sign, there are 3 broad approaches which are used in practice. These are called sign magnitude, 1's complement and 2's complement representations. Now, we shall be explaining these 3 representations one by one. These are all used to represent signed numbers, numbers which are both positive and negative. Let us look at the simplest first, the sign magnitude representation. You see, the sign magnitude representation conceptually looks like this. Suppose I have an n bit representation, this whole thing is n bits. So, I reserve 1 bit for this sign, this is my sign. The remaining n minus 1 bits will represent magnitude. So, as a matter of convention we can follow this. In this sign, 0 means the number is positive, 1 means the number is negative. So, the most significant bit or MSB in short it is called, it represents the sign which can be 0 or 1, 0 is positive, 1 is negative. And the remaining n minus 1 bits will represent the magnitude, and already we know that in n minus 1 we can represent a number in the range 0 up to 2 to the power n minus 1 minus 1. So, the magnitude can be in this range. So, in this representation the range of numbers can be, sign will indicate whether it is positive or negative, but the maximum magnitude can be 2 to the power n minus 1 minus 1. So, the smallest number will be this, the largest number will be this, right. This follows directly from the binary representation. But there is one issue here, you can see that in this representation 0 is represented by 2 different bit patterns, because for the number 0 the magnitude obviously will be 0. So, these will be all zeros, but the sign can be either 0 or 1, it does not matter, because one will indicate plus 0, other will indicate minus 0, but technically speaking both are zeros, right, plus 0 or minus 0. So, one drawback of this representation is that one bit pattern we are wasting, we are using up 2 different bit patterns to represent the same number 0. Okay. This is one small drawback in this representation. So, this table shows you the sign magnitude representation in 4 bits. if it is 4 bits, you see the first column represents the MSB, most significant bit is 0, which means the numbers are positive, and the last 3 bits indicate magnitude. 0 0 0 is 0, 0 1 1 is 3, so on, 1 1 0 is 6, 1 1 1 is 7, and second column indicates where the most significant bit is 1. 1 indicates the number is negative, but the magnitude is again ranging from 0 to 7. So, you see that you can represent a total of 15 distinct numbers, because plus 0 and minus 0 are having 2 different representations, and on one side I can represent plus 1 to plus 7, on the other side minus 1 to minus 7. So, 14 plus 1, 15 total numbers I can represent. Okay. Let us come to 1's complement representation. So, what is 1's complement representation? In this method, if the number is positive, then it is represented exactly like in sign magnitude form, no difference. The first bit indicates sign, which is 0, and the remaining part represents magnitude. But negative numbers are represented in a different way, that we shall see. Suppose I have a number minus 5. So, I do something called 1's complement of 5, 1's complement of 5. So, it is explained what is 1's complement. So, once I do 1's complement of 5, this is my representation for minus 5. So, when I have a negative number, I take the magnitude 5, I compute something called 1's complement of 5, and that will give me my representation of minus 5. So, what is 1's complement? It is very simple. You take the number, let us say you have 5, let us say in 4 bits 5 is what, 0 1 0 1, this is 5, right, in 4 bits. You complement every bit of the number, that means 1 you make 0, you make 1, 1 you make 0, 0 you make 1, 1 you make 0. You change or flip every number, and this will be your 1's complement. This 1 0 1 0 will indicate minus 5, right. Now, you see here again the most significant bit will indicate sign, because when you do this, the plus 5 was having the most significant bit as 0, but as we flip it, it has become 1. So, for negative numbers the MSB will automatically be still 1. So, just by looking at the most significant bit, you can tell whether the number was positive or whether the number was negative. Okay. So, this table shows you the representations in 1's complement form. For the positive numbers, as I said, they are same as the sign magnitude form 0, 1, 2, 3, 4, 5, 6, 7. But for negative numbers, it is a little different. Well, here I have worked out one. Let us say I want to represent minus 4. I want to represent minus 4. So, how do I do it? I first take plus 4. What is plus 4? Plus 4 is my 0 1 0 0. I take 0 1 0 0. Then I take 1's complement of 0 1 0 0. I flip the bits. 0 becomes 1, 1 becomes 0, they become 1 and 1. So, it is 1 0 1 1. This way you can take something, let us take minus 2. 2 means 0 0 1 0. So, therefore, minus 2 will be, take 1's complement 1 1 0 1, you see minus 2 is 1 1 0 1. So, in this way you can calculate for everyone. So, here again you will see that there will be 2 distinct representations coming from 0. Plus 0 will be having the representation 0 0 0 0, minus 0 will be having representation 1 1 1 1, because you take plus 0 make negative 1 1 1 1, both represent 0. So, here again one of the combination is wasted, just like sign magnitude. So, it is mentioned here, range of numbers that can be represented here is just like sign magnitude form. Maximum is plus 2 to the power n minus 1 minus 1, minimum is minus 2 to the power n minus 1 minus 1. Because you look in the previous one, in the positive side it was plus 7, negative side also it was minus 7. Okay. So, plus for n equal to 4 it becomes 2 to the power 3 minus 1, 7 minus 7. And also this I mentioned that there will be two different representations of 0. But one big advantage is there, this of course we shall not be discussing now, we will be discussing later, that one big advantage of 1's complement representation is that when you do subtraction, you do not need to separately subtract numbers, because you can subtract numbers using addition only. So, what does it mean? Well, in a computer system we have both addition circuits, we have both subtraction circuits. Now, we are saying that if we represent our numbers in 1's complement form, we do not need subtractor circuits. We can have only the adder circuits. Using adder we can do addition, we can also do subtraction. This is a big advantage. So, we shall see later how this is done or how this is achieved. Okay. Now, let us move on to the third representation, 2's complement, which in fact is an extension of 1's complement, and in fact this is the most widely used representation today. So, here again the positive numbers are represented as in sign magnitude form. For negative numbers, you represent them in something called 2's complement form. Now, what is 2's complement form? The definition is simple. Well, earlier we had seen what is meant by 1's complement, just flip all the bits, you do 1's complement, then you add 1 to the number. This is defined as 2's complement, right. Complement every bit of the number and then add 1 to the resulting number. So, here again the most significant bit will indicate the sign, 0 for positive, 1 for negative. Let us see how the representation works. So, again an example for n equal to 4. So, for the positive numbers it is same as sign magnitude or 1's complement form, no difference, but for negative number there is a difference. Let us again take the example for minus 4, plus 4 is 0 1 0 0. So, when you want to represent minus 4 like here, we have to take the 2's complement of plus 4 is this, 0 1 0 0 was plus 4. You first take the 1's complement. 1's complement means you flip the bits 1 0 1 1, 1 0 1 1 means what in decimal, 8 plus 2 plus 1 13, 8 plus 2 plus 1 11, you add 1 to it. So, we shall be talking about rules of addition later. If you add 1 to it, it will become 12, 12 is 1 1 0 0. So, 1 1 0 0 will be the representation of minus 4. Right. Now, another advantage here is that, well, if you just look at the issue of 0, earlier we had the issue of 0, there are two representations. Okay, let us try to compute minus 0. What is minus 0? You take plus 0, you take the 1's complement, add 1 to it. if you want to add 1 to it, you will see that in 4 bits the result will again become all zeros, which means minus 0 will also be having the same representation. So, there will be no 2 separate representations of 0. But what will this extra combination indicate? Here I can add one additional number minus 8. This combination 1 0 0 0 will indicate minus 8. This we shall see later also how this is coming, but in 2's complement this is one advantage. On the negative side I can represent one extra number, on the positive side 0 to 7, in the negative side minus 1 to minus 8. So, the first difference is that the range of number is increasing by 1. On the minimum side we can represent one extra number, and this is because we have a unique representation of 0. And just like 1's complement, we can here also we can do subtraction by addition, and as I said, almost all computers today use 2's complement representation. So, when we talk about representing negative numbers today, so invariably we shall be talking about 2's complement representation. Okay. Let us talk about a few other features of 2's complement representation. Well, this may not be very obvious, but when you are calculating the value of a 2's complement number, this can help. Suppose I have a n bit number, I have a n bit number representation in 2's complement. Let us say in 4 bits I take 2 examples, let us say 0101 and let us say 1101. I want to find out its value. So, a simple rule is each bit position will be having weights, you add them up. Most significant bit will also be having a weight, but negative. So, when I talk about 0101, 0 multiplied by anything is 0. So, the value will be 0 plus 4 plus this again 0 plus 1, which is 5, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. But here, because the most significant bit is 1, it will be minus 8 plus 4, 0 is 0 plus 1. So, this comes to minus 3. So, you can check minus 3, you take plus 3 is 0011, take the 1's complement, add 1, it becomes 1101, the same 1101. So, this is a very quick way of finding out the value of a 2's complement number. You again follow that weighted sum principle, only for MSB the weight is negative, this is the only difference. Okay. The other interesting thing is that when you have 2's complement representation, so if you shift left a number by k positions, this is equivalent to multiply the number by 2 to the power k. Let us take some example. Let us say in 8 bit representation I am showing plus 19, this is 1, 2, 4, 8 and 16. So, 16 plus 2 plus 1 is 19. So, if I shift left the number by 2, that means 10011 is getting shifted and 2 zeros are inserted on the right. So, if you evaluate this number again 1, 2, 4, 8, 16, 32, 64. So, 64 plus 8 plus 4 becomes 76. So, 19 multiplied by 4 is 76, 2 to the power 2. So, even take the case of negative numbers, minus 29 is this, you can check this is minus 29. Shift left by 2, shift left again 2 zeros are inserted, it is minus 116. So, minus 29 multiplied by 4 is minus 116. So, shift left by every position is equivalent to multiplying a number by 2. If you shift left twice, multiply by 2 square. Similarly, if you shift right, it means dividing by 2. If you shift right by k position, it means dividing by 2 to the power k. So, again an example, this is a number, this represents plus 22, this you can check. If you shift right by 2, zeros will be inserted on the left. So, this becomes 5. So, 22 divided by 4 is 5 point something. If you ignore the decimal part, it is 5. But only one thing, if the number is negative and when you shift right, you shift the sign bit, do not shift zeros, you pad it with the sign bit. Because the number was negative, let the number remain negative. So, it was minus 28, shift by 2, this number becomes minus 7, this you can check. So, again we are dividing by 4. So, shift right means division, shift left means multiplication by some power of 2. And one last trick, let me tell you, that just as this example shows, means some sort of. So, you can replicate or copy the sign bit as many times as you want without changing the value of the number. This is called sign extension. Like you consider an 8-bit number, let us say plus 47. In 8 bits, this is plus 47, you can verify 1, 2, 4, 8, 16, 32, 32 plus 8 plus 4 plus 2 plus 1. Now, suppose I want to represent this number in 32 bits. So, I have this representation and I add 24 zeros in the beginning. This is called sign extension. So, you can check this number will also represent plus 47. The same thing holds for a negative number also. The only rule is that you are replicating the sign bit, not adding 0 like here. The sign bit was 1. This is the representation of minus 93, this also you can check. So, you can replicate the sign bit so many times, your number will remain still minus 93. So, when you change the size of a number, you can freely replicate the sign bit and add it in the beginning as many times you want. This is a big advantage of 2's complement representation. Okay. So, with this we come to the end of this lecture. So, we shall be continuing with our discussion in the next lecture again. Thank you.